This is called the extreme value theorem. If f is continuous on a closed interval, alright, so a few things right off the bat here. Continuous, the function has to be continuous, and you have to consider this theorem on a closed interval. If you have an open interval, it fails, okay? It has to be continuous and on a closed interval. This closed interval is AB. Then f attain an absolute maximum f of c and an absolute minimum f of d at some number c and d in the closed interval AB. Right. So for this extreme value theorem, it say that if the functions has these two conditions, it's continuous functions and it's on a closed interval, then I could be able to find an absolute maximum and an absolute minimum. Then you're always going to be able to find an absolute maximum and an absolute minimum. Further note here, functions continuous on the closed interval. This means that the functions continuous on a closed interval always attain extreme values. That's the first note. The second note is functions need not possess extreme values if either continuous or closed interval conditions is omitted. Right, so in order to see this second note, a function needs not possess extreme values if either continuous or closed interval condition is omitted. So I give you two graphs to indicate this note. Right, so this function is clearly discontinuous. Right, so therefore you cannot find an absolute maximum or absolute minimum at all. Okay, so I want to note here, f is discontinuous at x equal to 1. The functions has an absolute minimum, but no absolute maximum. So the next graph I want to give you is, so you see that the functions is actually continuous, but it's continuous on an open interval. So the functions is continuous on an open interval 1, 2. Right. It's continuous on an open interval 1, 2. It's continuous, but it's not a closed interval. So therefore, you cannot identify specifically the absolute maximum or the absolute minimum. Right? But has no absolute, or even stronger statement, no max or min values at all. No matter where you consider the point, you cannot be able to find the absolute max or maximum value or minimum value at all. So the maximum minimum appear at the point where we have the horizontal tangent line. So each has a slope 0. Right? The slope is related to the derivative. Right? So that is f prime of c is equal to 0 for some constant c. So that means most of the time what we're looking for the derivative of the functions and evaluate the derivative at the point
c such that f prime of c is equal to 0.
Fermat's theorem. So for this theorem, it say that if f has a local maximum or minimum at c, and if f prime of c exists, then f prime of c is equal to 0. All right. So if you have a maximum, you have a minimum, and if the derivative at that point you are considering is does exist, then f prime of c is equal to 0. I want to note that we must be careful when using Fermat's theorem, because even when f prime of c equal to 0, there need not be a max or min. There may be an extreme value even when f prime of c does not exist. I'm going to give you two examples to indicate this notes. So go back to the Fermat's theorem. It say that if f is the local maximum or minimum at c and f prime of c exists, then f prime of c is equal to 0. That's just one direction. The directions say that if f is the local maximum and local minimum, and if f prime of c exists, then f prime of c is equal to 0. But when f prime of c is equal to 0, it's not a guarantee for you to have a maximum or a minimum. I will indicate that in an example here. Example, consider the functions y equal to x cubed. Say that to find the extreme value, when you try to determine the extreme value, take the derivative of the functions and set that equal to 0. Find the extreme value we set f prime of x equal to 0 and solve for x. Right. So f prime of x is equal to 3x squared. We set this equal to 0, and let's give you x equal to 0. And you could say that, okay, f prime of 0 is f prime of x is equal to 0, then x equal to 0. What about f of 0? Right? So f of 0 is also equal to 0. And you say that, okay, I find a point, right? Because normally I see that there's the horizontal tangent line there. Right? It's a good indication to have the maximum and minimum. Right? However, not in this particular case. Right? Yes, you can find f prime of x equal to 0. You can determine x. And you can determine the output as well. But the graph of the functions is this. This is cubic functions. Right, so at x equal to 0, there's no maximum or minimum at all, even though you still be able to find f prime of x. So that's one example to see that you have to be careful when you consider the Fermat's theorem. It's good indications when you do see a maximum or a minimum, but it's not a good indication when you just have f prime of x equal to 0. All right. The second conditions for Fermat's theorem is that if the derivative at that point exists. Okay, so what I'm going to do is I'm going to give you another example. So for this example, I'm consider the functions f of x equal to absolute value of x, and take derivative. But in order to find, right, the maximum value or minimum value, we set we take derivative, set that equal to 0, see what happened. However, when you look at the graph of the absolute value of x here, the functions is not differentiable at x equal to 0. Makes sense, right? Because we learned about this, we learned that because this is a corner, this is a kint, it's not differentiable. But still, to be able to find that there is a minimum. There is still an absolute or local minimum at x equal to 0. Right? The Fermat's theorem say that yes, the derivative has to exist, but in this case, it's not differentiable, but still there's a minimum there. So overall, does Fermat's theorem work? So we have to ask ourselves that questions because we have two examples that completely disprove this particular Fermat's theorem. So I could say that Fermat's theorem does suggest that we should at least start looking for extreme value at the number c, where f prime of c equal to 0. It may not work all the time, but at least let's start from that point. Let's start from there and see what happened, right? Or where f prime of c does not exist. Right. So two places to start. First of all, look at the extreme value where you have f prime of c equal to 0. It may not work. It's good. It's a good indication there might be a maximum or minimum. And another place is where f prime of c does not exist. Right. Go back to the example of absolute value of x in this case. The f is not differentiable at x equal to 0, but still be able to find a minimum. And a second note, first Fermat's theorem can be rephrased as if f has a local max or min, let's see, then c is a critical number of f. So another new terminology here, critical number. So when you have critical number, then you might have a maximum or minimum. All right, so what is the critical number? Definitions. Critical number. A critical number of a function f is a number c in the domain of f such that f prime of c equal to 0 or f prime of c does not exist. Right, two things you need to consider. Right? It depends on the function, of course, but the critical number is where you have f prime of c equal to 0 or f prime of c does not exist. Most of the time, people get this. Students get this. F prime of c equal to 0, you can solve the critical number. But the majority of time, people miss this. F prime of c does not exist. Sometimes you have to consider that. Go back to the example of absolute value of x. You need to consider that. Example, find the critical numbers of the functions f of x equal to 3x to the fourth minus 16x cubed plus 18x squared. All right, critical number, take the derivative and see what happens. Right, so the domain of these functions is all real numbers, right? Because this polynomial function, so the domain is always all real numbers. Take the derivative of the functions f prime of x what do you get here? You get 12x cubed minus 48x squared plus 36x equal to 0. And let's try to solve for x in this case. Right. So this is the cubic functions, but we can simplify this or we can factor this. Right? So x is the common factor. 12 is also a common factor. So you have 12x times x squared minus 4x plus 3 equal to 0. You can factor the quadratic expressions inside the parentheses. You have 12x times x minus 3 times x minus 1 equal to 0. So you solve this equations, you get x equal to 0 or x equal to 3 or x equal to 1. Right, when you solve the equations. But for the conclusions, when you make the conclusion, you see that the critical numbers are x equal to 0, x equal to 1, and x equal to 3. So you have 3 critical points. The next example is find the critical numbers of f of x equal to square root of x plus 1. Right. So first, find the domain of the functions. So the domain of the function is x plus 1 greater than or equal to 0, or x is greater than or equal to negative 1, or you can write from negative 1 to positive infinity. Now, to find the critical number, first take the derivative of the functions. F of x, you can turn this into a power functions like this, right? X plus 1 to the power 1/2 is a lot easier to take for you to take the derivative. So derivative of x plus 1 to the 1/2 is 1/2 times x plus 1 to the 1/2 minus 1. Right, so that's the outside part. The inside part is x plus 1 prime. So you have 1/2 times x plus 1 to the negative 1/2 times the derivative of x plus 1, which is 1. Right, so that's it. You rewrite this particular derivative as 1 over 2 times x plus 1 to the positive 1/2. Right? And in terms of a square root, you can write 2 times square root of x plus 1. So what is the domain of this derivative functions? So domain of f prime is x plus 1 is greater than 0. Right. So normally you have x plus 1 greater than or equal to 0 for the square root or for the radical functions, but it's still in the denominator, so that's why you have to drop the equal sign. Right. So you have x plus 1 is greater than 0 or x is greater than negative 1. Right. Or you can see that the domain is from negative 1 to positive infinity, but do not include the endpoints in this case. Right. So that's give me that idea that the function is not differentiable at x equal to negative 1. So it implies that f(x) is not differentiable at x equal to negative 1. Right? So therefore, the critical numbers is x equal to negative 1. Right? Because of the critical definitions of the critical number, you say that if you have f prime of x equal to 0 or f prime of c is not defined.